NASA is actively exploring a groundbreaking propulsion technology with a core objective: sending a probe to the Centaurus star system within 40 years. This leap could fundamentally redefine humanity's understanding of cosmic accessibility. Yet, interstellar travel remains a distant dream due to the unimaginable distances between stars, forming an almost insurmountable technological and energetic barrier that severely limits deep space exploration. However, the future 3-propellant interstellar propulsion system TIPS could accelerate scientific probes to nearly 1/10 the speed of light, about 30,000 kilometers per second. This velocity, beyond current spacecraft capabilities, would mark humanity's first reach into star systems previously deemed unreachable. But how does this SCIF-like technology work? Can its underlying principles withstand real-world physics? What key innovations could transform the vast, isolating distances of space into traversable pathways for human civilization? Might journeys to distant stars and exoplanets transition from science fiction to routine technological milestones within our lifetime? Join us as we delve into how NASA's breakthrough engineering concepts and physical implementations are gradually unlocking the door to an interstellar era, laying the theoretical and technological foundation for future space travel. In a thrilling new discovery with profound implications for our understanding of cosmic life, the James Webb Space Telescope, one of the world's most advanced deep space observatories, has detected dimethyl sulfide DMS in the atmosphere of exoplanet K2-18b. On Earth, this complex organic molecule is produced almost exclusively by biological processes, making it a key potential biomarker for life. Astrobiologists view this as one of the strongest indirect evidences yet for extraterrestrial life, particularly given K2-18b's likelihood of hosting a global liquid ocean, a water world capable of nurturing complex life. Imagine a future where advanced interstellar propulsion systems enable us to launch a research probe to K2-18b, equipped with high-precision instruments to confirm alien life or even capture images of extraterrestrial civilizations, finally allowing us to see our cosmic neighbors. At just 124 light-years from Earth, K2-18b is a cosmic next-door neighbor, though this distance remains abstract to most. Contextualizing it, across the Milky Way's 100,000 light-year diameter, 124 light-years is merely 1/1000th of that span, practically arm's length in astronomical terms, making it a prime target for interstellar exploration. Yet even this cosmic neighborhood is unreachable with current technology. A light-year 9.46 trillion kilometers exceeds the maximum flight range of any spacecraft. Consider the Voyager probes. Launched in 1977, they've traveled nearly 50 years but have covered less than a light day, a fraction of the distance light travels in a single year. Voyager 1's speed of 61,500 kilometers per hour, 17 kilometers per second, is impressive by aerospace standards, capable of crossing Earth's atmosphere in minutes, but glacial by cosmic scales. At this rate, reaching even the nearest star would take tens of thousands of years, far beyond any mission's feasibility. K2-18b is far from the only exoplanet intriguing scientists. Dozens of nearby celestial bodies, identified by ground and space telescopes, exhibit atmospheric, orbital, or compositional traits suggesting untapped clues to life. Many boast Earth-like environmental parameters, including Proxima Centauri b, discovered in 2016 by the European Southern Observatory. Orbiting Proxima Centauri, a red dwarf in the Alpha Centauri triple star system, it lies just 4.2 light-years away, the closest exoplanet to Earth. Its proximity and potential habitability make it the top priority for humanity's first interstellar mission, a tangible first step in technological breakthroughs. Yet an inescapable reality remains. With humanity's current propulsion resources and aerospace technology, even the most advanced probes would take 17,000 to 80,000 years to reach Proxima Centauri b. This timeline not only far exceeds the duration of any existing space mission, but also spans almost the entire lifespan of human civilization as we know it. However, looking to the future, particularly considering the theoretical potential of next-generation revolutionary propulsion systems, we may finally breach this temporal barrier, compressing what was once a utopian journey from tens of millennia into mere decades, and ultimately transforming interstellar travel from fantasy into technological feasibility. Let's now delve into the core principles of NASA's Sunbeam propulsion system, a cutting-edge concept viewed as a key breakthrough for future interstellar flight. Among all human-made spacecraft, no mission has surpassed the speed of NASA's Parker Solar Probe, which not only set a flight speed record but also provided invaluable insights for deep space propulsion. For instance, while orbiting close to the Sun, the Parker probe achieved a staggering 692,000 kilometers per hour, the fastest man-made object in history. Its trajectory, diving into the Sun's gravitational well, offered critical data for testing propulsion system limits. Yet even this incredible velocity pales in comparison to the 100 million kilometers per hour required for interstellar travel, nearly 150 times faster than current records, a stark reminder of the technological leap needed. Though this target speed sounds like science fiction, it is the actual propulsion goal set by NASA for its Sunbeam interstellar concept, symbolizing science's efforts to translate fantasy into realizable physics. At 30,000 kilometers per second, 10% the speed of light, a probe could reach the Centaurus system in 40 years, a journey once spanning millennia compressed into a single human lifetime, marking a historic shift from impossibility to accessibility. But how does the Sunbeam system achieve this? What scientific concepts underlie its acceleration principles? Conceptually, the three-propellant 3P propulsion system is deceptively simple. It abandons traditional reliance on onboard fuel and instead uses external energy for continuous thrust. A key innovation of the 3P probe is its lack of conventional fuel. Instead, it relies on sustained energy input from ground or orbital platforms for remote acceleration throughout the mission. This drastically reduces the spacecraft's mass and boosts propulsion efficiency. Traditional fuel systems are impractical for deep space, but Sunbeam envisions cosmic gas stations, external platforms emitting high-energy particle beams to continuously power the probe, enabling steady acceleration. Crucially, Sunbeam's ultimate goal is not just launching lightweight microprobes, but deploying 1,000 kilograms glass research detectors equipped with full scientific instruments and communication systems, capable of real-time data collection and transmission for genuine deep space research. The system's backbone is relativistic electron beams, high-speed electron streams accelerated close to light speed, providing both kinetic energy and directional stability for interstellar energy transfer. In simple terms, Sunbeam uses particle accelerators to fire near light-speed electron beams at the probe, delivering sustained thrust over time to traverse interstellar distances. These electron beams are not emitted from Earth, but from solar satellites' external acceleration platforms positioned in close solar orbits to harness solar radiation for power. Solar satellites would use solar radiation pressure and magnetic fields to maintain orbit and orientation, continuously firing focused electron beams at the probe. Multiple satellites could act as distributed energy stations, delivering pulsed electron beams to accelerate the spacecraft in stages, eliminating the need for onboard fuel. The longer the electron beams act, the more momentum the probe gains, gradually approaching its theoretical speed limit of 10% light speed over years of flight. A critical challenge arises. In the vacuum of space, would high-speed electron beams disperse like mist due to Coulomb repulsion between negatively charged particles? Modern physics offers a solution through relativistic length contraction from Einstein's special relativity, which enhances particle beam collimation from the moving system's frame of reference, mitigating divergence over vast distances. In simple terms, time dilation refers to the phenomenon where time within a high-speed moving system appears to slow down from the perspective of a stationary observer. This effect becomes particularly pronounced at speeds approaching the speed of light and is a key prediction of special relativity. A common example: if you observe a spaceship moving near light speed, the clock on board would appear to tick significantly slower to you. This principle also applies to quantum acceleration structures, especially in maintaining particle beam stability. When applied to the 3p3 propellant system, time dilation means that relativistic electrons retain stronger focusing capabilities within their own frame of reference, allowing particle streams to remain stable, concentrated, and precisely targeted at the detector over interstellar distances. If the ambitious 3P propulsion concept is realized, humanity will achieve, for the first time, journeys to other star systems within a reasonable timescale, enabling us to verify whether exoplanets of scientific interest truly harbor life-friendly environments. This would revolutionize our understanding of life's distribution in the universe. As previously noted, one of the top priorities is Proxima Centauri b, the closest exoplanet to Earth and our most likely candidate for early in situ exploration. While scientific models suggest Proxima Centauri b is tidally locked with one side perpetually facing its star and the other in eternal night, creating extreme temperature differences, it orbits within the habitable zone, where liquid water could theoretically exist, a core indicator of habitability. The habitable zone is the orbital region around a star where a planet's distance allows water to remain liquid on its surface long-term, providing foundational conditions for carbon-based life. For Proxima Centauri b, scientists speculate that a terminator zone, the boundary between day and night, might offer relatively stable temperatures where liquid water could persist, serving as a critical ecological buffer for life. However, it's essential to note that current observational data remain insufficient to confirm these hypotheses, whether liquid water exists or if even primitive life forms have emerged on Proxima Centauri b awaits direct verification by on-site probes. Deploying interstellar detectors is thus not just a technical challenge, but a necessary step to address the fundamental question of whether life in the universe is unique. While the 3P system is a promising concept, it is not the only serious interstellar propulsion proposal. For example, the Breakthrough Starshot initiative takes a different approach, aiming for miniaturization and extreme lightweight design to achieve interstellar travel. Backed by world-renowned physicists like the late Stephen Hawking and Freeman Dyson, its core strategy involves launching microchip-sized nanocraft equipped with light sails, accelerated by high-power laser arrays from Earth or orbit. In contrast, NASA's Sunbeam system, with its focus on deploying heavyweight research detectors near the Sun, offers more controllable costs and the ability to carry sophisticated scientific instruments, providing irreplaceable advantages in data collection and remote operations. A critical question remains: when will this exciting technological vision take its first substantive step? How close are we to the first interstellar launch? When might the first 3P-based probe depart Earth on its epic journey to Centauri? This is a key timeline of interest to both scientists and the public. However, realizing this grand plan will not happen overnight. We must acknowledge the significant technical and engineering challenges ahead. Before launching the first Sunbeam detector, patience and strategic focus are essential. Though the Sunbeam system is theoretically sound and ambitious, its propulsion method is unprecedented. Core components like relativistic electron beam generators and remote energy platforms must be developed from scratch, requiring precision alignment capabilities across light years. Even micrometer-level angular errors at interstellar distances would cause particle beams to miss the target, dooming the mission. Thus, ultra-high directional accuracy is not a luxury but a prerequisite for success. Another key challenge is energy dissipation and material tolerance. Maintaining effective particle beam transmission over vast distances requires exponentially increasing energy output. Meanwhile, solar satellites deployed near the Sun must withstand extreme temperatures, electromagnetic radiation, and cosmic particle impact, stretching current materials science to its limits. Thankfully, despite these challenges, several core technical modules of the Sunbeam system have already undergone preliminary validation in laboratories and related engineering projects, bringing us closer to this vision than might be imagined. For example, the Large Hadron Collider LHC operated by CERN is already capable of generating high-energy particle beams far exceeding the requirements of the 3P system. Its accelerator technologies in particle energy, magnetic confinement, and vacuum stability provide a critical reference blueprint for 3P. Additionally, the multi-dimensional beam guidance systems used in modern particle accelerators have achieved a high degree of maturity in sub-millimeter trajectory precision control, which could be adapted and scaled into interplanetary particle beam positioning and spacecraft locking systems. Another example is NASA's Parker Solar Probe, which has successfully approached the Sun and maintained stable operation in high-temperature and high-radiation environments. This mission demonstrates that we have accumulated valuable experience in heat-resistant materials and thermal shield technology. However, it's important to note that the thermal-to-electric energy conversion systems required for Sunbeam, particularly large-scale energy capture and conversion based on thermoelectric generators, currently remain in the theoretical phase. with no mature prototypes yet deployable on actual solar orbital platforms. In other words, we still lack a complete engineering solution for stable solar orbit operation, long-term solar energy capture, and efficient conversion into particle beam energy output. These orbital power plants remain in the concept validation stage and are decades away from practical application. Realizing this grand vision faces to fundamental limitations, unresolved core technologies, and enormous budgetary requirements. Beyond R&D funding, international coordination, engineering test cycles, and policy support will profoundly influence its progress. Thus, even under the most optimistic projections for technological development and budget allocation, the first experimental prototype vehicle based on 3P propulsion principles is expected to take at least 20 to 30 years to design, test, and launch. But here's the good news. While waiting decades for the Sunbeam probe, you can click the subscribe button now and in less than 30 seconds gain instant access to our latest updates on cosmic exploration, deep space technology, and interstellar futures. Thank you for watching. We'll continue bringing you the most cutting-edge insights into space exploration and technical analysis. Stay tuned for the next exciting episode. See you tomorrow.